Good afternoon, ladies and gentlemen. I am Zeng Yanan from Tianjin Agricultural University in China. It's my pleasure to give the talk today. My topic is the movement measurement of particle with high resolution based on combined digital holographic microscopy. The contents are divided into 4 parts. First one, we come with the introduction part. The topic is about the particle movement. The particles are commonly utilized as contrast agents in bio and non-biological imaging applications. We are concerned about the particle displacement. For example, these particles are embolized in the HT1080 cells. They are used to measure the refractive index of cytoplasm in the cell. Then the displacement measurement of particles is important. All the targets of the displacement measurement we concern most are the resolution and the three-dimensional. We need to measure the displacement with high resolution. For the geometric size of a given particle may lie at micro or even nanometer scale, so the high resolution is required, mainly nanometer scale. And three-dimensional measurement is also important, which can be divided into 2 questions about in-plane displacement measurement and along the optical axis displacement measurement. The in-plane displacement measurement has already reached the nanometer scale or even sub-nanometer resolution because the feature shape of the particle, namely the circular shape, can be fully utilized in image processing. But the displacement along the optical axis is not as easy to bring to the nanometer scale. Digital holographic microscopy, DHM, is an effective, commonly used approach to particle tracking. The advantages are non-invasive, non-contact refocusing, and so on. For the DHM applied in the particle tracking or the displacement measurement along the optical paths, there are mainly the inline DHM and off-axis DHM. The inline DHM are widely used for the measurement of out-of-focus particles, and the resolution is high. Researchers have got 1 nanometer resolution. But there is a problem in inline DHM, which is the in-focus or nearly in-focus particles cannot be measured by inline DHM. The reason is that the twin image problem limits the measurement. The twin image, the effect of the twin image can decline the measuring precision. Researchers have attempted to solve the problem by using dual cameras or phase-shifting devices, but the setups are complicated and the measurement processes is unstable. For off-axis DHM, the twin image problem can be avoided. Because the twin image frequency spectrum can be separated from the real image frequency spectrum. After judging the focus condition of the reconstructed intensity with refocusing algorithms, the displacement along the axis can be measured by tracking the most in-focus particle in the off-axis DHM. Researchers concerned about the image sharpness, structure tensor, edge sparsity, or the magnitude differential method to realize the refocusing algorithms. Yet, a long-axis measurement resolution in the off-axis DHM is lower than that in the inline DHM, normally reaching the micrometer scale resolution. To improve the resolution, in our research group, we proposed an optical path length variation method. The resolution is improved to 10 nanometers, but we can see that it's not as high as the 1 nanometer resolution in inline DHM. Then we can summarize that the inline DHM and off-axis DHM are both have pros and cons. The pros of inline DHM is high resolution, but the cons is obvious too. The inline DHM are unable to measure in-focus particle. The pros of off-axis DHM is both in-focus and out-of-focus particle can be measured, but the cons is that the resolution is low. The highest resolution of off-axis DHM is 10 nanometers. So today we propose a technique which combines the pros of both inline and off-axis DHM, but avoids the cons, namely the combined digital holographic microscopy, the CDHM. The CDHM make full use of the pros, but avoid the cons to make sure that the high resolution can be obtained, and both the in-focus and out-of-focus particles can be measured. At the experiments on the silica particle movement, we can see that 5 nanometer resolution for in-focus particle and 2 nanometer resolution for out-of-focus particle can be reached. Then how to realize the high resolution and the both in-focus or out-of-focus particles can be measured? Here comes the methodology. The CDHM, both in CDHM, both off-axis and inline DHM, digital holograms can be obtained in one setup. This is to see 2 holograms, one setup. The setup is the off-axis digital holographic microscope. As we can see that the off-axis hologram is easily to guide, but the inline hologram, how to guide the inline hologram from an off-axis hologram? we use an AFRM method, namely the interference fringes removing method, to isolate inline hologram from off-axis hologram. Then two holograms can be obtained. Here comes another question. Which hologram is to be reconstructed? Let's tell some details. Here comes the CDHM flow diagram. We get the off-axis of a hologram. By using the off-axis reconstruction, the reconstruction distance can be obtained. We compare reconstruction distance to critical reconstruction distance, which we named CRD, a new parameter. If when the reconstruction distance is equal to CRD, the twin image impact on particle center intensity is narrowed in 5%. That is to say, if the reconstruction distance is larger than the CRD, the hologram is selected for reconstruction. To calculate the axial displacement of particles, which the intensity impact of the twin image on reconstructed intensity can be neglected. But if the reconstruction distance is smaller than CRD, the twin image impact cannot be neglected. If the twin image impact can be neglected, then we can conclude that the particle is out of focus. Then inline DHM can be used to calculate axial displacement. To make full use of the pros of inline DHM, the high resolution. If the reconstruction distance is larger than CRD, the twin image impact cannot be neglected. Then the particle is in focus or nearly in focus. Then off-axis DHM is utilized to calculate axial displacement. But the cause of off-axis DHM is still existed. Then how to improve the resolution of off-axis DHM is another question. Then here comes three questions. First one, how to remove the interference fringe from off-axis D hologram, which is also the question how to get the inline hologram from off-axis hologram. The second question, how to calculate CRD. This is also the question, which hologram is to be reconstructed. Then the third question, what is the method to improve off-axis DHM? Then we propose a method named ring pixels of optical path loss method. We will solve the three problems one by one. First one, the AFRM method. The spectrum components located at non-center positions in the frequency spectrum of hologram are the interference spectrum of object beam and reference beam. Namely, in the space area, these are the intensive interference fringes. Therefore, the center spectrum of off-axis hologram is the spectrum of inline hologram of the particles. Then the inline hologram can be isolated from the off-axis hologram by filtering the central spectrum components. We can see that in figure 3a, The magnified part of the yellow square is shown here. There are interference fringes, very intensive. Then we use IFRM method. In the magnified part, the interference fringes are removed. Then we get the inline digital hologram. Then here comes the second problem, how to calculate CRD and the CRD calculation. First, we tell the principle. The twin image impact is the principle to calculate the CRD. The twin image impact on the particle center intensity should be narrowed within 5%. Then we analog the sample particle of the transmission rays. The sample particle is a spherical particle, silica. The diameter is 5 micrometers. The particle can be seen as a special lines. And the maximum intensity point is the focus point of the lines. Therefore, the intensity along the axis can be analyzed to assess the severity of the impact of the twin image. As we calculated the probability in density of locations where the incident beams and optical axis intersects, we can the focal length. The biggest probability density is lying at the 10.69 micrometers position. That is to say, the focal length of the particle length is 10.69 micrometers. Then the intensity distribution along the z-axis at the particle center is shown in figure 6 and 7. The particles shown in figure 8a was recorded out of focus. Therefore, the twin image intensity distributed as a reconstructed image plane is so low that the impact of the twin image is negligible. The figure 8b. But for figure 8a, conversely, the particle is recorded nearly in focus. At the reconstructed image plane, the impact of twin image is not negligible. So the intensity ratio of the twin image to the real image at the reconstructed plane can be calculated as follows. To quantitatively assess the impact of the twin image, according to the 95% confidence interval theory, the RTR should be 5%. Therefore, in the sample particle, the CRD should be 50.6 millimeters. Then we solve the third question. What is the RPOPL? And it is also the question how to improve the off-axis DHM resolution. In figure 9a shows the optical path length of traced rays through particle. In AA section, the OPL value decreases as the incident angle increases. But in BB section, it appears as incident angles increase, but the OPL value is not just increased nor decreased. Therefore, an inflection point must exist in relationship between OPL difference. Then tracking the displacement of inflection point is to measure the axial displacement of the particle. We used to measure the OPL values, but in today's talk we use RPOPL. Instead of calculating only 2-point pixels of the OPL, which we mentioned in the previous work. The technique we propose today is to sum the ring pixels of OPL and analyze the difference. The RPOPL comprises more information than only 2 pixels, and the problems caused by the OPL by the inclined transmitting beam is also avoided, while the average effect of the ring pixels makes the RPOPL more representative, thus permitting more precise measuring results. We can see in Figure 10 the RPOPL difference simulation. In Figure A, an inflection point can be found in the RPOPL differences between various rings and central pixel, and the ring 7 is most obvious among the rings shown here. And if we calculate the second derivative of 7th ring, revealing a peak, which can serve as a tracking marker to measure the particle movement displacement along the optical axis. That is the RPOPL method. We can verify our methodology by experiments. We use the pair apparatus shown in Figure 11. This is a classical digital off-axis digital holographic microscope. We get a digital hologram first of a particle. The tested particle is here. We use the angular spectrum reconstruction method to calculate the reconstruction distance, which is 29.5 mm. As we mentioned above, it is larger than CRT. Then we can know that the particle is an autofocus particle. Then we can use the inline DHM technique. We use IFRM to isolate the inline hologram, and we use angular spectrum reconstruction to reconstruct the intensity. We get the reconstructed intensity, and we move the particles along the axis for these parameters. And we get the relationship between the intensity of particle center and the reconstruction distance. If we see the frame 100 and frame 150, we can see that the reconstruction and the intensity of particle center is moved too. As the reconstruction distance differences, the particle center moves. The intensity of particle center moves too. If we track the intensity maximum point, then we can track the particle along the optical axis Then here comes the displacement along the optical axis of outer focus particle. We can say that it is in accordance with the particle movement. First, it go down 10 nanometers and go up 5 meters, and go down 5 meters and go down 5 nanometers. And then the displacement along the optical of the focus particle can be shown in Table 1. From the results, we can conclude that if the reconstruction distance is larger than CRD, the CDHM resolution along the optical axis should be 2 nanometers. Then we test another particle. This particle is nearly focused. You can see that in this figure 13A. Then we reconstruct the digital hologram. The reconstruction of figure 13A is 9.3 millimeter. It is smaller than CRD. Then we can conclude that the particle is a nearly in-focus particle. Then the inline DHM technique cannot be used. The particles were moved along the Z-axis. Then we use the off-axis DHM technique, namely the RPOPL method mentioned above. If we use the RPOPL difference above, then we can draw the displacement along the optical axis of nearly in-focus particle. We can see that the first way the particle is go up to 20 nanometers and go down 20 nanometers and go up 10 nanometers and go down 10 nanometers and so on. Then we calculate the details and we get Table 2. Displacement along optical axis of nearly in-focus particle. From the result, we conclude that if the reconstruction distance of particle is smaller than CRD, the resolution along the optical axis should be 5 nanometers. Then we can see if the particle is moved along 5 nanometers, we can get the difference. But if it is smaller than 5 nanometers, we can't measure the difference of the particle position along the optical axis. Then we come to a discussion. From the experiments, we know that tracking the maximum intensity of the particle's center pixel to locate each particle's axial position is not sufficiently precise. And the radius of the particle must have a length of at least 3 pixels. This limits the size of the particle under analysis. And the third one, the proposed method is only applicable to spherical transparent particles with known radius and refractive index. Because the theory is based on the law of refraction and simulation. At last, we make the conclusions. The CDHM improves the measurement resolution of the in-focus particle to 5 nanometers, and the resolution of out-of-focus particle measurement is 2 nanometers. Based on the CDHM, the resolution of axial displacement measurement of the particle reaches the nanometer scale, and both the in-focus and out-of-focus particles can be measured. Here is all the talk about. Thank you for listening.